Welcome to Math with Professor V. In this video, I will be working through and solving the most recent exam. I gave my Calculus 3 class all on multiple integrals as well as the Jacobian and change of variables. So we're going to be doing double and triple integrals in rectangular, cylindrical, and spherical coordinate systems. If you need an introductory video lecture on any of these topics or a more in-depth lesson, I have the full-length video lectures linked in the description. I'm just going to work through and solve this entire exam in one go. And if I were you and I was reviewing for an exam or something, I would pause it and try to solve each of the problems on my own first and then see how you did. All right, first question. Evaluate the integral by reversing the order of integration. You must also include a neatly labeled sketch of the integration region 2D. So I was super nice. I wanted them to know that they needed to reverse the order of integration. Let's figure out what this region looks like that we're integrating over in the xy plane. So outermost limit is x. Therefore, the limits that bound the region in the x direction go from 0 to 1. They match the outermost integral. And then the limits for y, see how that's next? They go from rad x to 1, rad x to 1. So let's graph what this looks like. We're just going to be in the first quadrant. Here's my y-axis, here's my x-axis. X is bounded between 0 and 1, and y from rad x to 1. So hopefully you guys are all comfortable. Rad x is, yes, top half of a sideways parabola. Now here's the key part. X being bounded from 0 to 1 tells me I'm, okay, in this region, somewhere in here. Y is bounded below by rad x, above by y equals 1. So let me add y equals 1. And then you have to decide, where am I shading? What is the region? Well, it's up here. It's this portion. And what I always tell my students, if they have a rough time figuring that out, you're trying to figure out the limits for y. Draw an arrow in the y direction through the region. Where it enters first is the lower limit. That's y equals rad x. Where it hits second, that's your upper limit, 1. Okay, very good. Now I want to reverse the order of integration. So that means on the very outside, I want dy. So the limits for y need to be constant. Whatever differentials on the very outside, that variable's limits have to be constants in order for you to get a constant as your answer. So y is going to go from 0 to 1. And then now to figure out the limits for x, you can do the same little trick with drawing the arrow. It's just this time I'm going to draw an arrow in the x direction, you see? Okay, well, where did it hit first? That's at x equals 0. And then where does it hit second? Well, this is y equals rad x. But I need to solve for x. X is equal to y squared, okay? Enters at x equals 0, exits at x equals y squared. Are we good? Okay, now let's set up our integral. So outermost limits are still 0 to 1. Limits for x are 0 to y squared. Then you have square root y cubed plus 1, and now the order is dx dy. Now there is no algebraic trick to looking at the limits of integration and figuring out what they should be when you reverse them. You have to graph. You just have to. So embrace it. Okay, now here's where the beauty of the problem comes in, because for a moment you were stuck, right? Like nothing in our power would help us evaluate this integral. However, now, I'm just integrating with respect to x first. I don't see an x. So then, treat square root of y cubed plus 1 as a constant. Pick up an x, antiderivative of 1, basically. Evaluate it from 0 to y squared dy. And then you have integral 0 to 1, square root y cubed plus 1 times y squared minus 0 dy. Are we okay? And then let me rewrite it. 0 to 1, y squared, square root y cubed plus 1 dy. And then from here, you can just do a relaxing little u sub, or you just do it in your head. Right? You go, if I let u be y cubed plus 1, du would be 3y squared. All I have is 1y squared, so I'm going to pick up a 1/3. Then I have y cubed plus 1. If I take the antiderivative, I'm going to add 1 to the exponent. I need to divide by that exponent. and then evaluate from 0 to 1. And then this ends up being 2/9 times 2 rad 2 minus 1. Good? Okay, perfect. First one's done. Next, change the Cartesian integral to an equivalent polar integral and then evaluate. You must include a neatly labeled graph of the integration region. So we're going polar. Notice again, same idea. So the limits for y on the very outside go from 0 to natural log of 2, and x goes from 0 to the square root of ln of 2 squared minus y squared. Hopefully you recognize this is the right half of a circle, radius natural log of 2. If you're like, Professor V, I don't see that. Let's generalize. When you have x equals square root a squared minus y squared, square both sides. Can you see now? This is a circle centered at the origin, radius a. And then when you solve for x, the positive radical gives you the right half of the circle. The negative radical gives you the left half of the circle. Okay, so we can easily sketch out this integration region, and then we'll use the graph to help us switch to polar. So here's x-axis, y-axis. I'm just going to sketch a whole circle, and then we'll decide what's the appropriate part to shade based on the limits of integration. The radius here is ln of 2. Don't fret. You're going to love that it's ln of 2 in a hot second. So y is bounded between 0 and ln of 2. So y equals 0 is here, all the way up to ln of 2. So above the x-axis. But then notice x is bounded from 0 up until the circle. So x is bounded from 0 up until the circle. So we're actually only dealing with 1/4 of the circle, the portion that's in quadrant 1. This is the region right here. So let's bound it. The limits for theta, if we're in quadrant 1, measure it the way you always measure theta. 0 up until pi over 2, very good. And then the limits for r, you can do the same trick with drawing the arrow. It's just for r doesn't go up and down, r is measured radially. So start from the origin, draw an arrow just outward, away. So it started at 0 and it ended at the circle. What's the circle's equation in polar? If it's centered at the origin, it's just r equals whatever the radius is. So r will be going from 0 to ln of 2. Are we okay? Very good. So here we go. So this integral becomes the integral from 0 to pi over 2, 0 to ln of 2, and then e to the square root of x squared plus y squared, that's e to the square root of r squared, dx dy is r dr d theta in polar. Perfect. Okay, all my limits are constants. I don't see any thetas, so then I can just, I mean, I don't do this part often, but you can think of it like it's 0 to pi over 2 d theta, and then you have 0 to ln of 2. This is e to the r times r dr. And then what I always tell my students is you're just going to pick up a theta and evaluate it from 0 to pi over 2. So all that ends up happening is you multiply by pi over 2. And I honestly don't need to see this step. If you look here and there's no thetas and these are all constant, then just slap a pi over 2 on the front. That's what I always tell them. Yes, just move on with your life. Okay, 0 to ln of 2, r e to the r dr. That looks cuter to me. We got to do tabular. Well, by parts. You can do it traditionally. This one's just beautiful for tabular. So whatever u would be, you differentiate r1 until you get a 0. And then dv is what you integrate, e to the r, e to the r, e to the r. And then you take products on the diagonal. If you don't know tabular, oh my gosh, I have a great video for you. It'll help you so much. It's life-changing. Okay, and then let's see, what are we left with? That pi over 2 is minding its business. R, e to the r, minus e to the r, evaluated from 0 to ln of 2. So now we have pi over 2 times natural log of 2 times e to the natural log of 2 minus e to the natural log of 2 minus 0 plus e to the 0. So these e to the ln of 2's are 2's. This is a 1. And I have pi over 2 times 2 ln of 2 minus 2 plus 1, which is pi over 2 times 2 ln of 2 minus 1. I would just leave it like that. I would. I hate that this 2, it's kind of how my mom writes her 2s. It looks good with her handwriting, but I didn't like it. Okay, good. Hopefully that one wasn't too bad. Okay, next one, still polar. Use a double integral to find the area of the region inside r equals 18 sine theta and outside r equals 9. You must include a neatly labeled graph of the region. Okay, both of these are circles. This is a circle centered on the y-axis. Why do I know that? Because it has a constant times sine theta in it. So the radius of this circle is 9 and the center is at 0, 9. Great. And then r equals 9, that's another circle, radius 9, but this one is centered at the origin. So when you just have r equals a constant, it's centered at the origin. If you have r equals some constant times sine theta or some constant times cosine theta, then it's centered on the y-axis or the x-axis. Okay, before we draw our graph, we have to find where they intersect. So we're going to set 18 sine theta equal to 9. Then I get sine theta is a half. So that happens when theta is pi over 6 or 5 pi over 6. Perfect. Now let's draw these two circles. Okay, that's probably perfect right there. X, Y. Okay, one circle is centered on the y-axis. And then the other one is centered at the origin. And they have the same radius, radius 9. So this is at 9 and then this is at 18. So this outer circle, this one's 18 sine theta and then this one's just r equals 9. So we want the area of the region inside 18 sine theta and outside the other circle. So we need this piece here. Whew. Okay, and we're asked to use a double integral. So you're not doing this Calc 2 style. So the area is going to be double integral dA. We have to figure out what are the limits for theta and what are the limits for r, because I'm certainly not about to attempt to do this in rectangular. Heavens no. So for theta, you have to figure out what angles bound the region. And that's precisely why we found the intersection. This is pi over 6 and this is 5 pi over 6. So theta goes from pi over 6, like there's no area here, so don't start at 0. Pi over 6, keep going, keep going, keep going, up until 5 pi over 6. And then what about r? So just do the little arrow trick. Start at the origin, draw a ray outward. Where it goes through first is the lower limit of integration. Where it hits second is the upper limit. And you could do it in any direction. You draw that arrow radially outward for r. Lower limit, upper limit, lower limit, upper limit. Lower limit's 9, upper limit 18 sine theta. Okay, so here we go. So the area is going to be integral pi over 6 to 5 pi over 6. And then 9 to 18 sine theta, and then dA in polar, be careful, it's r, dr, d theta. Perfect. Now, some things to make your life easier. Since this area is symmetric with respect to the y-axis, and that happens when theta is pi over 2, I'm going to double it and then integrate from pi over 6 to pi over 2. Only because I'm thinking at the end, I'd much rather plug in pi over 2 for theta than 5 pi over 6 when I'm doing my computation, okay? That's just personal preference. Okay, moving on, let's integrate. Antiderivative of r is 1/2 r squared, and then that's evaluated from 9 to 18 sine theta, d theta. Great, I love it, I love it. The 2, the 1/2, they cancel. Then we have integral pi over 6 to pi over 2, 18 squared sine squared theta minus 9 squared d theta. I can factor out 9 squared, which is 81. Then I have pi over 6 to pi over 2. If I take 81 out of 18 squared, I'll be left with a 4. So 4 sine squared theta minus 1 d theta. And then, yep, replace sine squared theta with 1/2 times 1 minus cosine 2 theta. And then I have 4 times 1/2, so that's 2. So then that's 81 pi over 6 to pi over 2. And then don't forget you have 2 minus 1. 2 minus 1 is 1. And then minus 2 cosine 2 theta d theta. And then from here, let's see, we'll have 81 theta minus the 2 will cancel when I take the antiderivative, sine 2 theta from pi over 6 to pi over 2. And you should end up with 81 times pi over 3 plus rad 3 over 2. Boom. Good? Okay. Next problem deals with surface area. So find the area of the surface for the part of the hyperbolic paraboloid, aka our beloved saddle, that lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. You must include a neatly labeled graph of the integration region, so just a 2D graph. You do not need to graph the surface, so you don't need to graph the saddle. So when you're finding surface area, what you do is you evaluate double integral of just ds. And how do we define ds? For now, the only way we know is that if you have a function of x and y, it would be equal to partial with respect to x squared plus partial with respect to y squared plus 1 dA. Whatever you're finding the surface area of, in this case, the saddle, that's what I'm going to use to find ds. These cylinders tell me which portion of the saddle I'm finding the surface area of, obviously not the whole thing. So they determine my integration region. These give me the bounds, okay? So let's go ahead, let's find ds first, and then we'll graph the integration region, figure out what the limits are. So partial with respect to x is negative 2x. Partial with respect to y is 2y. If I substitute those in here, partial with respect to x squared is 4x squared. Partial with respect to y squared is 4y squared plus 1 dA. As soon as I look at this, I'm thinking, we're probably going to go polar because I see that x squared and the y squared. And sure enough, I'm thinking to myself, oh yeah, this is going to be the region that I'm integrating over. We can easily represent it using polar coordinates. Definitely don't want to stay in Cartesian land. Get me out of there quick. Okay, so we've got x squared plus y squared equals 1. And then we've got x squared plus y squared equals 4. That looks good. Pretend they're perfect. All right? Yes. And we just want the area of the saddle, the surface area of it that lies above this donut here. This lovely little donut. What's your favorite kind? You know, I like an old-fashioned. I know everyone's all into the yeasted donuts, but I love a good old-fashioned donut. Okay, so if we were to integrate over this region, and I'm going to represent it with polar coordinates, theta is going to go from 0 to 2 pi, right, all the way around. And then r, r is going from 1 to 2. 1 to 2, people. Here we go. Now, can we switch this to be in terms of polar? You betcha. This is square root 4r squared plus 1. And what's dA? R dr d theta. Thank goodness for that r. It's going to save the day. Otherwise, we'd have to trig sub. Did you catch that? No. Okay, you're just blissful and going through your math class so happily. Okay, so we're going to have integral 0 to 2 pi, 1 to 2. Yep. Let me get ready for what's coming. 4r squared plus 1 to the 1/2 r dr d theta. So you know what I'm going to say, right? Straight away, slap a 2 pi on the outside. Yes. Then we're also going to simultaneously take the antiderivative. I know. Pretend you did a u sub, but don't do it. U is 4r squared plus 1. du would be 8r. All I have is a 1r, not an 8r. So I'm going to pick up a 1/8. Then when I integrate, you're going to add 1 to the exponent, divide by the new exponent, evaluate from 1 to 2. See, I'm done. See? So good. Okay. So what is this all going to simplify to? 4 over 24, so that's pi over 6. And then I have 4 times 4 plus 1 to the 3 halves minus 4 plus 1 to the 3 halves. And you can just leave it as pi over 6. 17 to the 3 halves minus 5 to the 3 halves. I know the back of the book writes 17 rad 17 and 5 rad 5, which is fine. It's not wrong. It's just, I don't care. You can stop here. Okay, next one. The figure shows the region of integration for the integral 0 to 1 rad x to 1, 0 to 1 minus y, f of xyz, dz, dy, dx. Rewrite this integral as an equivalent iterated integral in the 5 other orders. You must also include a 2D graph of each of the base regions for your setups. So there should be 2 graphs total, xy plane, yz plane, xz plane. So let's do the easiest reversal first. I'm going to keep the xy plane as the base and just switch it so that the outer 2 swap. And then we'll have to redo what our base region is. That's going to be a little bit more work, but we're good. We got this, guys. We got this. Like, if you don't move the dz, if you don't move it, then this can stay the same. So, yeah, here we go. Using the xy plane as the base. So x is bounded between 0 and 1, and y is bounded from rad x to 1. I feel like we just did this. Oh my God, we did. It was basically the first test question. Okay. So 1, 1, here's rad x. And then the region, though, is up here, right? Because y goes from rad x to 1. Oh, you should be ready to switch it so professionally because you just did it in the first question on the test, like I said. So if we're going to switch the order so that it goes dz, dx, dy, whoever is last, those limits have to be nothing but constants. So that one's going to go 0 to 1, and then x is going to go from x equals 0 to, that's x equals y squared, 0 to y squared. And then I'm not moving, like I'm leaving dz first, so we don't need to move that. So setup number 1 of 5 is going to be we'll have 0 to 1, 0 to y squared, and then don't touch this part. 0 to 1 minus y, f, dz, dx, dy. Boom. 1 is done, 4 to go. The rest will be harder. Okay, from here, let's do the YZ plane as the base next. So what does this region look like projected over the YZ plane? Like pretend you're standing here and you're just looking down at the YZ plane. All you would see is a triangle, right? You would just see z equals 1 minus y. That's all you see. Okay. So if the YZ plane is the base, that means the orders, we have 2 options. We're going to do dx, dz, dy, and dx, dy, dz. So the outer 2 determine the base, and then this is the height of the solid. Okay, so let's draw a little triangle, harmless little triangle. It doesn't have to be perfectly to scale, just we're trying to figure out what the limits are going to be and just have everything oriented correctly. Okay. Oh, I just want to color it in, guys. I'm just trying to color it in. Okay, so whatever variable or differentials on the very outside, those ones have to be constant. So y would go from, well, let me label this. Y, z, obviously. Y is going to go from 0 to 1, and z goes from 0 to the line. This is z equals 1 minus y. So 0 to 1 minus y. If you went the other way around, z would go 0 to 1, and y would go from 0 to this line, but this line is y equals 1 minus z if I solve for y as a function of z. So 0 to 1 minus z. That's it. Now the limits for x would be the same for both integrals. So how to figure out the limits for x. So you're going to pretend like you're standing back here behind it, okay? And you shoot a bullet through the solid in the positive x direction. I'm serious. Where the bullet enters the solid is your lower limit of integration, and where it exits is the upper limit. And it has to be x equals, okay? X a function of y or z, whatever. So it enters at the YZ plane, doesn't it? It enters at the YZ plane. So that's just x equals 0, okay. It exits at this surface here. This surface is determined by y equals rad x, but I have to solve for x instead as a function of y. It's exiting at x equals y squared. So x will go from 0 to y squared. Sorry to be talking about shooting bullets through solids, but it really resonates with my students, so I'm just keeping it real here. So you're standing back there behind the solid. You always have to shoot the bullet in the positive direction. So here's x-axis. It enters at x equals 0. It exits at this surface, which is x equals y squared. Okay, ready? We got 2 more. Look at us go. Okay, so 0 to 1, 0 to 1 minus y, 0 to y squared, f, dx, dz, dy. And then the other one is 0 to 1, 0 to 1 minus z, this stays the same, 0 to y squared, f, dx, dy, dz. Whew, very good. You ready for the last one? Okay, well, last 2 integrals, right? This time we're using, I need a page, guys. I need another page. We're going to be using the xz plane as the base. Okay, so what would that even look like? So that's maybe a little harder to imagine. So the xz plane, you have to imagine, say you're standing here and you're looking at the solid projected over the xz plane. What you're going to see is the intersection of y equals rad x and z equals 1 minus y projected over here. So in the xz plane, I'm going to eliminate y. I'm going to find the intersection of these 2 surfaces because they're tracing out basically, they're tracing out right here, this curve. I'm going to see that curve flat up against the xz plane. So I need to figure out where these guys intersect. It's not that hard. You can just sub in rad x right there, and it's z equals 1 minus rad x. Boom. Now the question is, can you graph z equals 1 minus rad x? Sure you can. Z equals rad x is like this. 1 minus rad x reflects it over the x-axis, and then this means shift it up 1. So I think you should be able to do it. You are in Calc 3 after all, right? Yes, you can do this. Okay, it's concave. Up, very good. Yep, don't screw that up. That would be upsetting. Okay, very nice. Now, if the xz plane is the base, that means x and z are the outermost variables. So the order would be either dy, dz, dx, or dy, dx, dz. So let's figure out what are the limits. Say we're doing y, dz, dx. So if x is last on the outside, those limits have to be constant. So x is going to go from 0 to 1. Z, just draw a little arrow through. Z goes from 0 to this curve, which is 1 minus rad x. So 0 to 1 minus rad x. Okay, what if we went the other way? So if z is on the outside, z's limits have to be constant, 0 to 1. Here's the trickier part. Okay, limits for x. Draw an arrow through the region. It goes from 0 to the curve, but you have to solve for x as a function of z. Ugh. Okay, so this is rad x equals 1 minus z, so x equals 1 minus z quantity squared. Okay, that's fine. We made it. Now, what about y? How do you figure out the limits for y? You look at the 3D graph. And what do? You pretend. Here, let me erase all the other stuff so it's not too messy for you all. you pretend, because we got to figure out the limits in the y direction. So you're shooting a bullet. Yep, sorry, that's what we're doing. You're standing back here. You shoot a bullet through the solid in the positive y direction. Where it enters is the lower limit of integration. Where it exits the solid is the upper limit of integration. It's entering at this surface here, which is y equals rad x. It's exiting at this surface here, which is the plane, y equals 1 minus z. Y equals 1 minus z. I'll say it again. Shoot a bullet in it. Enters at y equals rad x, exits at y equals 1 minus z. There you have it. Rad x to 1 minus z. Okay, let's set it up. 0 to 1, 0 to 1 minus rad x to 1 minus z, f dy dz dx. And then the other one is 0 to 1, 0 to 1 minus z squared, rad x to 1 minus z, f dy dx dz. There you have it. Okay, these take practice. All right, here we go. Setup only. Yeah, just set it up. The iterated integral for evaluating triple integral over d of f r dz dr d theta, so I'm telling them we're in cylindrical, over the region D, where D is the right circular cylinder whose base is the circle, r equals 6 sine theta, in the xy plane and whose top lies in the plane z equals 10 minus y. You must also include a 3D graph of the region D and a 2D graph of the base region. So let's do the base region. So the base is this circle, r equals 6 sine theta. Remember what I told you about that circle? It's centered where? Yes, on the y-axis. And what's its radius? 3, very good. Okay, so there's the circle. This is the base of the solid. So let's figure out the limits for r and theta, and then we'll put the 3D graph together, and we'll do the limits for z. This is the base. So theta goes from, please be careful, 0 all the way to, this is just pi, not 2 pi. If you do 2 pi, it's too much. Is there a circle over here? No, there is not. So don't get carried away. And then what about r? Okay. Yep, draw a ray. Start at the origin, draw it outward. Start at the origin, draw it outward. It goes from 0 to the circle. 0 to the circle. Notice it's not the same length everywhere. It's dependent on theta. 0 to the circle, 6 sine theta. R's limits are constants if the circle is centered at the origin. This one is not. Okay, then it tells me in 3D, this is the base in the xy plane. Okay, got it, z equals 0. And then the top is the plane z equals 10 minus y. So at 0 in y and x, z is 10, okay? And then it's going to go downward up until, if y is equal to 6, it'll intersect when z is 4. So let me show you what I'm talking about. Let me show you. We know in the y direction, the circle's going to extend all the way to 6, right? Okay. So 2, 4, 6, 8, 10. Let me draw the base first. Something like this. Try to make a little perspective. And then I'm going to draw the plane now, z equals 10 minus y. So like I was saying, if y is 0 and x is 0, it's going to hit the z-axis at 10. And then when I'm all the way over here at y equals 6, if I substitute in 6, I'll get z equals 4. So 2, 4, I scaled by 2. So it's going to be like this. So it comes down, but imagine basically what was happening. This was a cylinder all the way up. This plane slices it. So if you had a cylinder that was going all the way up and then it got sliced by a plane, this is going to be slanted here like this, and then there's this backside here. Okay, good. Kind of looks like some lipstick. Have you ever seen lipstick unrolled? Okay, so we got to set up the integral. I got my graphs. Here we go, people. Theta's on the outside, 0 to pi. Then we have r, 0 to 6 sine theta. Then we need limits for z. Shoot a bullet in the z direction. This one's maybe more obvious. Starts at z equals 0, goes until the plane, z equals 10 minus y, but we are in cylindrical, so you can't say 10 minus y. You have to say 10 minus r sine theta. There you go. So 0 to 10 minus r sine theta, f r dz dr d theta. Good? Great. That was fun. Okay. Find the volume of the solid that lies above the cone, phi equals pi over 3, and below the sphere, rho equals 4 cosine phi. You must include a neatly labeled. Now, I've taught my students to recognize this is a sphere centered on the z-axis, and the center is at 0, 0, 2. If you need more of a breakdown why, I have so many videos on spherical volume and all that, so go check it out. But basically, you're going to draw that sphere up here. It's not centered at the origin. If it was centered at the origin, it would just be rho equals some constant, okay? And then it's always, again, yeah, half that constant in the front is the radius. So we need the volume of the solid that's above the cone and below the sphere. And the cone is phi equals pi over 3, which will intersect at z equals 2. If you're not sure, where did I get that? Rho is 4 cosine, phi is pi over 3, so 4 times a half, which is 2. And when rho is 2, that would be coming from the radius outward, right? That would be rho right there. And that's also at z equals 2. Okay. So here's my cute cone. All right. We need the volume of the solid above the cone and below the sphere. Can you imagine what it looks like? I'm going to erase this extra part because it's making it look messy. It looks like a snow cone. Yes, 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 yes. Just do a cute little piece here. We've got a green snow cone for today, guys. Oh, yes. Here it is. Fantastic. Okay, so let's figure out our limits of integration. We're going to use spherical coordinates, theta. We're going all the way around. So 0 to 2 pi. Phi, you always measure starting at the positive z-axis. This is phi equals 0. Do we have the solid? Do we have the solid? Yes. Keep going. Keep going. Right here it stops. Where is that? That's phi equals pi over 3. So we're going to go 0 to pi over 3. And then what about rho? Start at the origin, draw a ray outward. Start at the origin, draw a ray outward. It goes from 0 to the sphere. 0 to the sphere. So 0 to the sphere for cosine phi. Perfect. Perfect. Okay, so then the volume's going to be integral. 0 to 2 pi. 0 to pi over 3. 0 to 4 cosine phi. If I'm finding volume, you just do triple integral dv. You don't add an extra function, an extra variable function. You just integrate one. So dv in spherical is rho squared sine phi d rho d phi d theta. And then, yeah, slap a 2 pi on there. You know what I mean? Then 0 to pi over 3. I'm going to integrate first with respect to rho. So this rho squared is going to become 1/3 rho cubed. We'll evaluate it from 0 to 4 cosine phi. And then we've still got sine phi d phi. Perfect. Let's take that 1/3 outside with the 2 pi over 3. Then we have 0 to pi over 3. 4 cubed is 64 cosine cube phi. Sine phi d phi. And then that'll be 128 pi over 3. Do we want that out there? Sure. 128 pi over 3. If I u subbed, u would be cosine phi, du would be negative sine phi d phi. And then I'm going to have a 1/4 cosine to the 4th phi. And then to account for the negative, let me go 0 to pi over 3. Okay, I know this was very aggressive, but also very correct. Okay, 128 divided by 4, that is 32 pi over 3. And then cosine of 0 to the 4th, that's 1. Cosine of pi over 3 is a half. Raised to the 4th is 1/16. 1 minus 1/16, that is 15 over 16. And the 16 cancels with the 32, giving me a 2. And then the 3 cancels with 15, giving me a 5. And I have 10 pi. Stunning. Okay. Moving on with our lives. Use the given transformation to evaluate the integral. I know, this is the Jacobian problem, and I took pity on their poor souls. I gave them a very, very straightforward one with no graphing. X equals 3u, y equals 6v, z equals 7w. Here's the triple integral. R is the interior of the ellipsoid. You do not need to include any graphs as part of your solution. So let's apply the transformation and rewrite everything in terms of u, v, and w. So if I apply the transformation to the boundary of R, I just need to figure out what the ellipsoid's equation is going to become in u, v, w space. So x is 3u squared over 9 plus y is 6v squared over 36. Z is 7w squared over 49. This all equals 1. And no surprise, you get u squared plus v squared plus w squared is 1. So this is a unit sphere centered at the origin, radius 1. Beautiful. Okay, let's figure out the Jacobian. So in this case, we have del x, y, z, del u, v, w. So we take determinant. Partial of x with respect to u is 3. The other two entries are 0. Partial of y with respect to v is 6. The rest are 0, and this is 0, 0, 7. And then here, when you take the determinant, you can just take the product of the diagonals. If you've taken linear algebra, you probably know that. If you haven't, then this might be news to you, but it is a game changer. So this is going to be 126. So that's my Jacobian. Okay, so this triple integral becomes triple integral over s of u squared plus v squared plus w squared to the pi times 126 du, dv, dw. But I still don't want to integrate over a sphere in UVW space. Ugh, right? Instead, we're going to do one more change of variables and go to spherical coordinates. Oh yes. So if I need the entire unit sphere, theta is going to go from 0 to 2 pi, phi 0 to pi, rho 0 to 1. So here we go. 0 to 2 pi, 0 to pi, 0 to 1. U squared plus v squared plus w squared would be rho squared to the pi. I have 126 still. And then in spherical, that becomes rho squared sine phi d rho d phi d theta. Okay, so let me take the 126 out. Also, I don't see a single theta in there, do you? Okay, so I'm going to slap a 2 pi on there. Then 0 to pi, those are the limits for phi. So I have sine phi d phi. Okay, that's going to be relaxing. And then 0 to 1 are my limits for rho. And I've got rho to the 2 pi times rho squared. So that's rho to the 2 pi plus 2 d rho. And then I already addressed 0 to 2 pi d theta is gone. That's here. We already did it. We're done with that. Okay, you all right? Good. 252 pi times antiderivative of sine phi would be negative cosine phi, but lately I'm not into the negatives. I just make it positive and I switch the limits. It makes me happier. And then antiderivative of rho to the 2 pi plus 2, well, you would add 1 to the exponent, making it 2 pi plus 3, and divide by that new exponent from 0 to 1. Okay. This is a constant. This is a constant. This is going to be what? Cosine of 0 minus cosine of pi. 1 minus negative 1. That's going to give me a 2. So 252 times 2 is going to be 504 pi out front, 2 pi over 3 in the bottom, and then I have rho to the first, or 1 to the 2 pi plus 3. Rho is 1 to the 2 pi plus 3 minus 0 to the 2 pi plus 3. So we're done. 504 pi over 2 pi plus 3. Okay, perfect. Love it. Moving on. It's getting easier from here on out. Don't worry. Evaluate. Following triple integral by transforming to cylindrical or spherical, you must include a neatly labeled graph of the solid, 3D only. Hopefully you can tell by now, XY plane, this is the entire circle centered at the origin, radius 3. Can you tell that? Because X goes from -3 to 3, Y goes from top half to bottom half of circle, radius 3. So that's the whole circle. That is the whole circle. I didn't need them to give me a 3D graph because hopefully this was so painfully obvious. That was my hope. I don't know. I'm actually recording this before they take the test. Okay. So, I'm feeling like we're probably going to go cylindrical, but I'm not sure. Let's see. Z goes from rad x squared plus y squared, that's a cone, to z equals 3. So it's probably easier if we stay cylindrical because the plane z equals 3 isn't so nice and spherical, and we actually have to evaluate this one, not just set it up. So I'm thinking, let's do cylindrical. However, if they wanted to do spherical, that's fine. That's fine. I would be shocked if any of them did it because it's not easier and it wasn't a setup only problem. So we've got our standard cone, z equals rad x squared plus y squared, which in cylindrical is z equals r. And then upper limit is z equals 3. So this is the top of the solid. These are the sides. And you could see this is the base region because pretend you're standing up here looking down. Yeah, exactly. You would just see this circle outlined, right? Of radius 3 in the xy plane. Okay, that's not the actual physical base. That's just the region that you're integrating the solid over. The solid lives above that region. Okay, so theta should go from 0 to 2 pi, r 0 to 3. I love it. I love it when they're all constants. And z is going to go from r to 3 because rad x squared plus y squared in cylindrical is r. Okay, so we'll have 0 to 2 pi, 0 to 3, r to 3, and then it's just dz dy dx. So that'll be r, dz dr d theta. We're going to slap a 2 pi on here. Yes, we will. Then we have 0 to 3. I don't see any z's. So if I pick up a z, I'll evaluate it upper limit minus lower limit. So that's 3 minus r, r dr. Look it. You could have done this back in kindergarten. Okay, it comes out to 9 pi. Good. Last one, set up only a spherical coordinate integral to find the volume of the solid bounded below by the xy plane, on the sides by the sphere rho equals 8, and above by the cone phi equals pi over 3. Ooh, you must include a neatly labeled graph of the solid. So I'm telling them it's in spherical. The solid is bounded below by the xy plane. That means the xy plane is the base of this solid. Xy plane is the base. It's bounded on the sides by the sphere rho equals 8. That sphere is centered at the origin. Rho equals 8. I'm not going to draw the whole thing because I already know it's bounded below by the xy plane. So let me not do too much. I don't want you to think there's more to the solid. This is the base. It's bounded below on the xy plane, by the xy plane. On the sides by this sphere, and then above by the cone, phi equals pi over 3. So say this is pi over 3. This is bounding the solid above. So the cone is above the solid. So the solid, yeah, exactly. It kind of looks like a bundt cake. It does. So imagine you had a dome and someone came and cut a cone out of it. Okay, some sort of bundt cake. Ooh, and we are in spherical. So here's your graph. This would be a full credit graph. Theta, we're going all the way around. All the way around. So 0 to 2 pi. What about phi? Be careful. You always start at positive z-axis. There's nothing, there's nothing, there's nothing. Now the solid starts at pi over 3. So pi over 3 up until they're solid, they're solid, they're solid. Ooh, it stops. Where are we? Pi over 2. We're at phi equals pi over 2. And then rho. Rho goes from origin out. Origin out. Origin to the sphere. Who's the sphere? Rho equals 8. 0 to 8. Boom. We need to find the volume. So volume is going to be triple integral dv. It'll be 0 to 2 pi, pi over 3 to pi over 2. You know, this would have been really easy to evaluate, but boring. Not showing me anything new, so I don't need to see it. I wouldn't get any new information about their math skills. So we're good. The graph is good. Their reading comprehension is really tested in this one. Okay, last one, extra credit. Set up a triple integral of an arbitrary continuous function in spherical coordinates over the solid shown. So let me redraw the solid over here, and I'll make it transparent because I think that's helpful. Here we go. X, Z, Y. The height is 2, and the radius is 3. Boom. And then this matches. Okay. Something like that, yes? Okay. If we're in spherical, we need to split this into 2 integrals. And you might say, oh, what makes you think that? Well, I'm imagining, okay, what would my limits of integration be for theta? That's pretty clear. It's just going to go 0 to pi over 2 because you see how this little wedge is in the first quadrant only. First octant, but that translates to first quadrant. I'm just coloring you guys for fun while I regrew. Okay. Yes, very nice. Okay, what about phi? That's going to change depending on how things are going. Obviously, it's from 0 all the way to pi over 2, but we're going to split it because rho goes from 0 to this plane here. 0 to the top of it. 0 to the top of it, right? Rho is determined by the top of this solid, which is z equals 2. And then later, after this exact angle here, which we'll find out, why did that not self-correct into a straight line? Whatever. Here, please correct thyself. Good. Now, rho is determined by the side. The side. Do you see that? Okay. The side has equation r equals 3. Okay. Okay. So we're going to have to set up 2 integrals, and we're going to split it basically right here at whatever value phi takes on here. You ready? Okay. So first integral, theta is going to go 0 to pi over 2. That doesn't change. Phi will go from 0 up until mystery angle. We can find the mystery angle. Don't you fret. I'm going to pop in a cute little right triangle here. Yes. This is 2. This is 3. Here's phi. This is the mystery angle right here from the picture. Boom. Do you need it in pink as well to believe me? Good. Okay, tangent of phi is 3/2. So that angle is tan inverse of 3/2. Okay, there you go. That goes right there. Tan inverse 3/2. Now, what about rho? Rho goes from 0 up until the top, which is z equals 2, but we're in spherical. So z is rho cosine phi equals 2, which means rho is 2 over cosine phi, or 2 secant phi. Good? 2 secant phi. Perfect. Integral number 2 will pick up where the other one left off. So theta is still going 0 to pi over 2. Phi will have to go from tan inverse of 3/2 all the way up until the solid stops here. That's phi equals pi over 2. And then what about rho? Rho goes from 0 to the side. The side is r equals 3. R equals 3 in spherical is rho sine phi equals 3, which is rho equals 3 over sine phi, or 3 cosecant phi. 3 cosecant phi. Boom. So that's our 2 integrals that we're going to have to set up. Some continuous function f, so I'll write f as a function of rho theta phi, and then you have rho squared sine phi d rho d phi d theta. So 2 integrals. So we have 0 to pi over 2, 0 to tan inverse 3/2, 0 to 2 secant phi, f of rho theta phi, rho squared sine phi d rho d phi d theta, plus 0 to pi over 2 tan inverse of 3/2 up until pi over 2, and then 0 to 3 cosecant phi, f of rho theta phi, rho squared sine phi d rho d phi d theta. If they just put f, that's fine, but they needed to have the correct dv for spherical to get it, to get the points for the extra credit. I do all or nothing for extra credit, so no partial. Okay, that concludes the exam. How did you do? What would you score yourself? I don't know how you grade, but hopefully you did well. And if you enjoyed this video, please don't forget to give it a thumbs up, share it with a classmate or whoever else you think might enjoy it. Don't forget to subscribe to this channel for more calculus lectures and fun. And you can also follow me on Instagram and TikTok, Math with Professor V. Thank you guys so much for your support. I love you all. I'll be back sooner than later.